so that we can make the most of the hour. You will know CNC Microsystems provides research infrastructure to the National Design Network, which is a network of researchers, students, collaborators, and companies across Canada. With this portfolio, which is accessible from our homepage at cmc.ca, we have a test equipment lending pool, which provides access to a number of high-performance measurement instruments and figures available to researchers on a short-term loan. Co-hosting the webinar today is Andre Boyu, Senior Technical Consultant at Keysight Technologies. Andre will feature a presentation on the basics of RF signal and spectrum analysis measurement techniques. Analyzer is a measurement workhorse in any RF test lab, and it's important to have an understanding of how it works and how to set it up to get the best measurements possible in your test applications. It is a Keysight E47B spectrum analyzer that we have in the test equipment pool. There are two Keysight DSA-N1021B signal analyzers available, one with to 13 gigahertz and the other to 26.5 gigahertz. As I will describe, the signal analyzer can operate as a spectrum analyzer, but has added capabilities for analyzing complex vector modulated signals. He is a senior technical consultant for the Electronic Products and Solutions Group of Keysight Technologies. He's responsible for the technical support training for Keysight customers. Andre has over 25 years of experience in the test and measurement industry. He HP, which became Agilent and then became Keysight a couple of years ago in 1994, as a technical consultant for the RF and microwave group. Recent activities have focused on supporting the Communications Measurement Solutions Division's products, and especially on the signal analyzer. He received his Bachelor of Science degree in Electrical Engineering from École Polytechnique of Montreal. I want to point out, as is seen on our introductory slide, that if you have any questions that you'd like to pose to Andre throughout the webinar, please feel free to use the chat box or the Q&A box, and we'll address these at the end of the webinar. Another delay, I'll hand over to Andre.
Thanks. Okay, very much, and welcome everyone to this signal analyzer fundamental and new application webcast. The signal analyzer in general is quite a versatile equipment. So in this hour, we're going to just touch the basic and get some important setup that you need to do in order to optimize your measurement and get the best measurement accuracy out of your spectral analyzer. If we look at the agenda today, we'll have first a little overview of going over what is actually measured using the spectral analyzer or signal analyzer, and also the technology about how it is working. The theory of operation, we're going to go into more detail on the traditional spectral analyzer, and at the end we're going to touch the modern signal analyzer. So basically going through the traditional spectral analyzer is allowing us to see the different setups that are available in the spectral analyzer, and how now the modern signal analyzer actually go and provide same functionality, but without hardware behind. We're going to touch the specification because you have to make sure that the equipment you're using has sufficient specification or in order to measure your signal, and we're going to look at some new application in some way. So James, I think we hear you typing, or someone, I don't know who it is, so I don't know if you can mute your phone, please. So if we look at some definition to start with, the spectrometer is commonly used, and this is what people are using. And I also make the mistake myself to interchange between spectrum and signal analyzer, but basically the spectral analyzer were used in the past to measure amplitude of the signal versus frequency. So it's a scalar measurement. It was the only thing the analyzer could measure. It was the frequency content of the signal as amplitude versus frequency. They could go quite high in frequency, but they were not able to do any kind of demodulation. With vector signal analyzer, now at the fixed IF, we could go and digitize a signal. And when we digitize the signal, we actually measure not only its amplitude, but also its phase. So we could go and demodulate complex modulation like QAM or in LTE signals. Then when we demodulate them, we are able to do some measurement like the error vector magnitude, some codomain power. We can measure spectral flatness, and we could also in some case apply some vector signal correction and some equalizer to see how the our receiver will perceive the transmitted signal. On the now, if you go on the website and you do a search, you'll find that we can now signal analyzer, and signal analyzer are really a combination of both the spectrum analyzer and vector signal analyzer. I have a tendency to interchange spectrum and signal analyzer, but in the course of this presentation, we're talking about the equipment that has the ability to do both measurements. If we look at the what analysis is really the ability to go and show the signal, like what we see on the bottom left corner of the display. Is actually a pole signal that is measured. You can see the sine over x kind of waveform, which is showing this way because it's in the logarithmic display. And on this side, we can see that, well, this could be a wide band CDA signal that we can actually capture. We can measure the adjacent channel power. We can do some kind of demodulation and actually get more information about the quality of the signal. On the last display, on the right side, what we have is a pure tone coming out of a transmitter, mostly either go to the fire or just maybe out of the synthesizer. And in this case, we can see that it has some harmonics, and in this case, this measurement would be the measurement of measuring the harmonic distortion of that signal going through a device. If we look at the what the analyzer allows you to do to actually take a signal that you can see on the left side, which would be the signal pulse that you would see on the oscilloscope. If you put your signal in the oscilloscope, and you can see the amplitude of the signal varies versus time. But the spectrometer on the other side, look at it on frequency content. It allows you to decompose the time domain signal into its frequency components. Sometimes it's useful. You see that the time signal in the oscilloscope might look like a perfect sine wave, because the dynamic range of the oscilloscope, which is 8-bit, only provides something like 50 dB of dynamic range, and you won't be able to see harmonics. Might be quite small. On the spectrometer, though, where the dynamic range is quite higher, you could discriminate and see that there are some frequency components that you can actually see that you wouldn't be able to see with the oscilloscope. It's two domains. This time, which is the oscilloscope, and the other one is frequency, which is on the spectrum analyzer. So I got a little animation here, was showing the signal propagate over time. You can see each of the frequency components that are seen, and they build when they in phase. You can see that pulse, and they subtract. And then you can see that little dip here. So that's what the spectrum allows you to do, to actually look at the amplitude of each of those frequency components versus, well, not versus time, but in the frequency domain. The oscilloscope will show to you in the time domain. So the time measurements that are available when you're using a signal analyzer are really quite a broad range. One would be spectrum monitoring. You would like to measure the output of your transmitter in order to make sure that you're not transmitting out on signal that will interfere with your neighbor or with other people which are sharing the frequency spectrum. Or you may have some signal that you are not aware of, which we call spurious, that your transmitter is transmitting. You want to make sure that they are below some specification. If you had a source, your spectral analyzer, you kind of make some scalar measurement. And this is actually good measure insertion loss in the case stable. It's not very accurate, but that's something that could be done. Since analyzers are quite sensitive tools, you can measure noise density, so you can measure amplifier noise figure, and it has application to measure local oscillator phase noise if you need to measure the device phase noise. So it was good to measure harmonics, so to measure that, or enter mod, because you have two carriers, they can enter mod, and you can have third order enter modulation, and we'll see that in more detail. And also, if you have FM modulation, digital bursts, you can look at them with the spectrum analyzer. It's a wide bandwidth detection, as you can see here, which allows to do vector signal analysis and allows to demodulate the signal so that not only you can see the power versus frequency, but you could also see the IQ diagram. The purpose of this is not to go over digital modulation. I think there's another one which is scheduled later on that will go over that. And here you can see that we are making a noise measurement. Talking of noise, now with the noise capability of the equipment, we can measure noise in a range of minus 172 dB, which is about a couple of dB above the thermal noise, which is 174 dBm per hertz, to a maximum in this case of plus 30 dBm. If you need to measure higher signal, then you need, of course, to put a pad in front of the instrument. As far as the frequency range, the analysis can go all the way down to 3 hertz, and can go have models that are going to up to 50 gigahertz from the front panel. But if you need to go higher than that, we have frequency extension or external mixer that will allow to go above a terahertz in frequency. Different ways of implementing this spectrum analyzer or signal analyzer. It will be to have a filter that will sweep in frequency, and as it's sweeping in frequency, we would notice, we would measure the amplitude of the signal at each of those frequencies. Kind of the way the equipment was built in the past using analog components, but it was not the filter, and we'll see later on, it's not the filter which is sweeping, it's rather the signal which is sweeping into the filter. Another approach is the use of an FFT analyzer. In this, the FFT analyzer could be looked at the equivalent of having multiple filter that are the signal at the same time. So why would we have both? Like on the analog, we have both. Well, looking at the wide span of frequency, a wide range of frequency, the FFT analyzer would be too slow to capture a little chunk of signal, calculate the FFT on each one of them, and then stitch them together. The FFT analyzer will be way faster, but I'm going to very, very small resolution bandwidth, like in the order of 100 hertz. Then it makes more sense to go to the FFT, and the FFT is faster. Instead of this signal analyzer, what you will see that they have an automatic mode, which it will automatically switch from SWIP analyzer to the FFT analyzer in order to either give you the fastest sweep or the best dynamic range. And these are setups you can make. You can say, well, I would like the analyzer to sweep for fast, for speed, or for accuracy. We'll look at the diagram of a traditional spectrum analyzer. So if we look at, here's the input of the analyzer. The first thing that the signal sees is the RF input attenuator. The attenuator purpose is to make sure the signal that will hit the mixer is too strong, because if that's the case, the mixer will start to create all kind of intermodulation. Then we go through a trace selector or the low frequency spectrum analyzer. They don't have this pass filter, they rather have a low pass filter, but as you're going to microwave frequency, we call this a pre-selector, and it's a back filter, which is filtering all the frequency might mix down to the intermediate frequency because multiple of the incoming signal. Then we have the mixer. The mixer combines the signal, the incoming signal, with the local oscillator, down converted or up converted to the intermediate frequency, which is the IF frequency. Then an amplifier was there to make sure that we crank the signal so that it will hit the detector at the right power level. So the IF gain here is coupled with the attenuator, so that if the attenuator is cranked up by 10 dB, the signal would look green if it would go down by 10 dB. In case the IF gain is cranked up by 10 dB, so that the signal remain at the same place on the display. The IF filter, which is commonly called the resolution bandwidth filter, because that filter actually is to discriminate signals. The narrower your resolution bandwidth filter, the more you can see details in the signal coming in. We'll see that there's a drop between the resolution bandwidth filter that you're using and the sweep time it takes to the analyzer to go through the frequency range you selected. We'll go out of the resolution bandwidth filter. It hit this log amplifier. The display on the spectrum is the logarithmic display. Then goes through this envelope detector. After that, it should be carrier should be taken away, and we should only have the envelope of the signal, which might have some noise still. That's where the video filter comes in, and that's low frequency filter, so it's filtering the frequency component, only leave the low frequency to pass through, and goes through the display. Generator is controlling the local oscillator to sweep the signal. It is also controlling the T, or in this case the time base, in order to show the frequency versus amplitude of the signal. A typical display spectrum analyzer. So the first, the reference level. The reference level describes the end of the signal at the top of the display. In this case, it is minus 20 dBm. After that, we have the amplitude scale, which is in this case 10 dB per division. So from the minus 20, calculate 10 dB down per division to measure the signal amplitude. As far as the frequency range, some people like to use a start and a stop frequency to define the frequency range, and others prefer to use a center frequency span. I would say that in general, when we're talking about spectrum analyzer, we're mainly talking about the center frequency and the span. At individual components, here we see a mixer. The mixer is a nonlinear device. It's the signal coming in, which in this case is at 0.5 gigahertz, and mixing it with the local oscillator. And at the output, since it's not nonlinear, we have a bunch of other components that are showing up. So we still have the signal coming in, we still have the local oscillator, but also have the subtraction of both and the addition of both signal. And in our case, we keep the which is the differential, or the subtraction of one from the other, as the signal that the analyzer is actually making. So it's not a filter that is moving. The filter is the resolution of the filter. It's fixed. It's really by sweeping this local oscillator that are making that signal move and go through the internal filter. I got a little animation later on that I'll show you. Now, the IF filter, or called the resolution bandwidth filter, we call it this way because if you look at those two size signal, or those two frequency components, if I use a wide IF bandwidth, I cannot see that there is to signal. As I narrow it, I start to see that, well, there might be something underneath here until I use a narrow enough resolution bandwidth, and I can easily see that there are components to this actual signal coming in. Let me tell you this now, and I might say it again on because it's kind of key. The relationship between the resolution bandwidth, the pick, and the time it takes to the analyzer to go through frequency range. And that's the relationship was, if you do the resolution bandwidth by a factor of 10, it will slow down the sweep time by a factor of 100. Today, with the digital filter that we have, with a modern spectrum analyzer, if you reduce the resolution bandwidth by a factor of 10, you slow down the sweep speed by a factor of 10. So that limitation If you go with a too narrow resolution bandwidth, that'll take a very long time to sweep through your frequency. So you have to use a filter just wide enough to allow you to distribute these signals. When you'll go through the filter, then it goes through this envelope detector, which is actually only keeping the magnitude of the signal and takes away the carrier component, which is the IF frequency. But at the detector, there are different kinds of detector. The detector in the spectrum analyzer actually captures signal or the signal faster, and it will capture way more points that you way. As an example, you can try to display 501 points on the screen, or you may want to display 1,000 points, but the analyzer will capture way more than that. So the question is, what do you have to do with all these extra values that are captured between two of the display points? And we call them bin buckets. Well, if you use the positive detector, then the analyzer will keep the maximum value that was detected during that period of time. If you use a negative detection, then it'll keep the minimum value that found during this capture. And if you use a sample detection, it'll use the value at that specific point. So the thing with the sample detection is the randomness of signal. And in that case, if you're measuring noise, that will be the best detector to use. Positive is mainly used to measure tones or that are continuous. Detection is used, and it's easy to see if the signal goes away. If you want that signal always there, or does it completely disappear at some point in time, that will be an application for that. And there's the average detector type, which is quite useful. So, well, I got all these points that will capture within a bin. So yes, of course, I can keep the peak or the negative, but I'm interested to read the noise on the display. I may say, well, I would like to use the average detector. It takes more time because those values are captured anyway. It's just what I really want to do with them. So in this case, it does a square root of sum of the square of those value and display the average. So that will be the average detector display. For the video filter, after the detector, you may still have some noise that remains on the signal, and that will have an impact. In case if I got a signal which is barely above the noise, I can set a gain by using a narrow video filter. It will kind of smooth the waveform. The noise level is not going down, but rather the phase is smoother. So the difference between doing average using trace average, where in trace average you capture a trace, then you capture a second one and average a value of them, and as you capture more and more traces, the noise kind of goes down. So that video averaging, like having an average which is on point per point as is sweeping. So it is slowing down the sweep, but converging to a nicer trace, a cleaner trace, and both will kind of give you the same final result. You have a little animation, which is that. So first, I had a signal in this at minus 90 dBm. It has no averages, so an average of 1. And what I will do, I will just go and change the average and enter an average of 5. And look at the signal here. You would see that the signal noise level went down a little bit. So if I go and I decide to go to 20 averages, now we can also see that there is something here popping up. So there was a signal in the noisy trace. If I go to 100, and here I will ask you to notice the power level here, because I'm going back to put an average of 1, which is no averaging, but in this case, I'll go and reduce the video bandwidth 1 kilohertz. When I do that, you see that the final trace, either by using the narrow video bandwidth, is almost identical and to the trace I got when I did 100 averages. So what difference? Well, if you look at the sweep time, here the sweep time in this case is 271 milliseconds, so about a quarter of a second. And start to play. Let me go to the 100 averages. You can see. Let me here. The sweep time was in 1 millisecond. 1 millisecond, but I need 100 traces to make that. So it depends what I want to achieve. I can go and use the video bandwidth or use the trace average. What you have to be careful is when you're using trace average, if your signal goes away, you'll go and fade out slowly. So the impression that your update is quick, but the signal will really show slowly. And if you're trying to do any kind of adjustment, that be misleading. The spectrum analyzer and the if we look at the black diagram, it's a simplified one. The actual signal comes in at 1.5, so it's the same signal. And we are going to combine it with the localizer here, which will go from 3.6 to 6.5. The frequency that we're going to look at, the intermediate frequency, is the frequency of the LO minus the signal. The filter here, which is our resolution bandwidth filter or our IF filter, sit at 3.6 gigahertz. So as the signal will, move, the LO will go from 3.6 to 6.5, and actually the 1.5 gigahertz signal will move, or difference of the LO minus that signal will move into the filter, and it will go through the filter. The detector will detect it, and we see it showing up on the analyzer display. Have a look at it. So here you can see the signal. Well, but I just moved it back a bit, so as you can see that as it is going through the filter, as it is at 3.6, we start to see it popping up on the display here. So let me continue. And of course, at the end, we have the signal versus frequency. So let me do it again. So signal versus frequency. And of course, we have that big signal here that shows up at the 0 hertz. And that is actually the oscillator feed through. Might be able to take it away, but it has been there, and people kept it because that's a big indication of where is your 0 hertz position on your display. So when you see a big signal, that's 0 hertz, and from that point you can move versus frequency, and then you can get your signal. I want to notice here is that, well, if we look at the signal coming in, which is a pure sine wave, and we got at the output is a kind of a filter shape, because really when that signal goes through the filter, it is a filter. And what the output is actually the signal which went through the filter. So it's always a combination. What you see on the spectrum analyzer is always a combination of the signal that in come with the resolution bandwidth filter. Because if you reduce the resolution bandwidth filter, you'll see signal here. Your input signal didn't change. Look at the modern signal analyzer. So basically, if you look at this part of the black diagram, it can exist. Well, it doesn't exist in its analog digital now. So signal comes in, it has this input attenuator. You have an option, get a preamplifier to, if your signal is too small, to amplify it before it goes to the mixer. But after that, the only thing you need is a filter that will select the appropriate signal out of the mixer. In our case, it was the LO minus the IF, minus the signal coming in was the IF. And after that, we just have a 16-bit digitizer, and it's only digitized. And of course, you have two modes. Either you go in FFT mode if you want to have a narrow resolution bandwidth on a large, or you can go in swept mode, which is ideal if you have to sweep through a wide frequency range quickly. All the resolution bandwidth is a digital filter. Because of that, it takes away a lot of the uncertainty that we had in the past. In the past, if you were changing the resolution bandwidth, there were switches that will switch the appropriate filter. And of course, there was an uncertainty in the switch, and there was also differences between the filter shapes. All of that is done digitally, so we control the shape of the filter, and there's no switching, so there's no uncertainty because of the switching. Then it goes to a digital log amplifier, which is perfect, close to perfect because it's digital. There's still some digital calculation error, but very small compared to the analog side. And then it goes to the digital detector to show the way you want it. So the big gain, they're modern signal analyzers like the DXA or the PXA, they have a 2-step attenuator. So that gives, in the old one had like 10 dB, which only gives you a coarse setup in order to optimize the signal at the mixer, and we'll see later on why that's key. We actually go up to 3 gigs to 50 gigahertz with wire that allow you to go at the level of minus 163 dB per hertz at 1 gigahertz. So, as I shared, the filter at the input, but after that, everything is digital, which allows us to have 160 different resolution bandwidth. And I think today we even have more. These are really digital filter. Most of the modern synthesizers now have digital synthesizer. So source, the frequency is way better. And the 16-bit analog to digital converter, which basically, well, it's 16-bit, but effectively in most, the maximum effective bit that we can have is 12.5 to 13. I haven't seen one that has 16 bits of effective bits. And the detector, we have a broad range of detector because they are all digital. So some of them, like the quasi-peak detector, is used for EMC AMI measurement. And you hear the uncertainty because of the digital log amplifier. It's like 0.07 dB. In the past, I think, well, we'll see. I have a slide on that, but it was way higher. We'll look at the specifications. That is the key point to direct you to the appropriate instrument. When people ask me which equipment I need to use, well, I ask them what is your signal, and there are a couple of questions about the noise level that you need, the phase noise that you need, the frequency range that are actually guiding through the kind of equipment that is required to make a measurement. So, for frequency range, you want to be able to go all the way up to the arm of your signal or the spurious that you need to find out the accuracy, and really you rely on it to understand that is coming out of your transmitter, and you have to rely on it. So it has to have sufficient frequency and amplitude accuracy, in resolution, in order to find out when you're looking at your signal if there are other signal close by, or if it's all the signal expected. Says D is you see small signal. How can you see a signal that is very, very small? The addition is the analog itself has some distortion. It will create some distortion below the distortion that you want to measure. Otherwise, there will be you'll have, and they will show up the spectrometer, and will show you. I'll show you a way of discriminating: are these distortion mine, or they belong to the analyzer later on. And the dynamic range, which is interesting because the dynamic range, we'll see that there's about half a dozen of different dynamic range. It's really the ability to see a small signal in the presence of a strong signal. How to measure a small signal when I also have a strong signal out of the analyzer. A couple of additions here. When you data sheet, when we that something is a specification, this is warranted. If it fails, you send it, we'll repair it under warranty. Usually the specifications are on a broad range of temperature between 0 and 55. Some that will specify if it is otherwise. The typical value, I think this is quite useful. Typical value, when we produce equipment, we test them and their performance. And we have a statistical database, and the typical value is valued at 80% of the units met, 90% with a confidence level of 95%, and they are usually at room temperature. They don't include the uncertainty of the equipment we use to measure them. So it's really typical value. It's quite useful, but if the equipment doesn't meet its typical value, it's not warranted. The specifications are level value that we expect the equipment to have. Some value, like example, the error vector magnitude of a digital signal, they're standard. It's not traceable to anything, so we cannot really provide a specification. So what we provide is nominal value, the local value if we measure that. Very, very important, especially if you borrow some equipment from DMC or from anyone, or even if it's yours, is to make sure that when you're connecting something to the front panel of the equipment, that you go and you read that little yellow sticker that tells you what you should and should not do. These equipment are static discharge sensitive. And people say, oh, I've done that 100 times and it didn't damage the equipment, and this time it did. Well, static discharge will not destroy automatically, in many cases, the equipment. The addition of multiple of those little charges will finally get through it. And where they can come from, well, when you have a cable, and you take a cable that is on a bench, that might have some chip built in. So it's a very good practice to go and connect the center pin of that cable to the ground to make sure that the cable is discharged before connecting it to the panel of the equipment. Also, you have to make sure that you're not exceeding this maximum RF power. When we say the power is plus 30 dBm, it's quite to plan your test system with a margin of about 3 dB. So you design and you pick the attenuator that you're going to use to make sure that the signal will not, in this case, as an example, exceed plus 27 dBm. And you have to ask yourself is, when I'm testing my transmitter, if the transmitter doesn't behave properly, what can be the maximum power? If it go and it start to oscillate, can I get more than what I think it will generate when it's working? So I would say a good rule of thumb is put some animation, put external pad when first, verify what you have, and then lower the power, the pad value. Also, always sustain any voltage when they are DC coupled. Some of them, and read that from the front panel, have capacitance which will protect them from DC, and in that case, they will sustain a certain level of DC. But when you go DC coupled, and you go straight and you bypass that capacitor, then you have to be careful. And usually, this is required when you're measuring signal below megahertz, because that capacitance at 10 below megahertz has an impact on the signal. And usually, when you're working at those low frequency, that there's a high risk of getting some kind of DC voltage to the signal. The frequency range, we have options for different equipment. In this case, you can go to 3.6 gauge. But look at the way the analyzer is built internally. For different frequency bands, with different arcs of the level oscillator. And as an example here, we use a fundamental to go from 3 to 3.6. We use band, we use the segmonics, and so on. That's why when you look at the noise floor of the analyzer versus frequency, you can see a little staircase on the noise floor as it is moved through the frequency range. And these are those noise levels are really caused by the fact that we're using the harmonics of the LO, therefore the noise floor goes higher because we're multiplying the noise of the local oscillator. If we look at the which are continuing to the frequency and amplitude currently, first at the input, there's the input match. Well, the input match, or the voltage wave ratio, is important because anything that is reflected back is not going to be measured. Well, to prove the return loss, or the input match, is to put an attenuator. But then you have to be careful, because if you switch the attenuator between two measurements, as I told you, make measurement between two different signals, and if you switch the attenuator, then you're introducing some uncertainty by switching the attenuator. The amplitude uncertainty. If you have the mixer input and the input filter here, that will have an impact on the frequency response, on the amplitude, but the frequency response of the signal. This attenuator will have an impact on the reference level accuracy. Resolution bandwidth filter will have a resolution bandwidth switching uncertainty, but we'll see that with the modern spectrum, it's at low. Then you have the lug amplifier, which creates the display scale fidelity uncertainty. The reference oscillator act on the frequency accuracy. And within the analyzer, the calibrator, and the calibrator is not perfect, and it's having some amplitude accuracy. So there are two kind of measurement. There's absolute and relative measurements, which are bringing the absolute and relative uncertainty or accuracy. So if we look at this signal here, and we put on it, that's an absolute measurement, and we're actually measuring the power and the frequency of that component. If we put a delta marker to next peak, that's a relative amplitude measurement and the frequency, and usually the accuracy might be a little better, and it is in general a little bit better, because when you do an amplitude measurement, it's not absolute. It's just relative to the calibrator signal. And the calibrator signal is at 50 megahertz, and it be measuring at 18 gigahertz. In that case, if you're measuring a signal between 18 and 18.001 versus measuring a signal at 18 versus a signal at 50 megahertz, then the uncertainty will be bigger if with absolute measurement in that case. Example of how, and that's interesting, because a simple question on like, what is the frequency accuracy of your equipment when I measure it? Well, we provide information, because there's no such thing as a single value. It's a matter of the marker or the frequency of the signal that you're reading. It'll depending on the frequency reference accuracy. In this example that we're looking at, the accuracy is 1.55 exponent minus 7 per year. And it depends on the span you're using to make your measurement. And go with 5% of the resolution bandwidth. In this specific example, that equation will change from analyzer to analyzer. There's 2 hertz visual error, and there is the error caused by the fact that you might be in between 2 points. So the horizontal resolution has an impact. In this, the horizontal resolution is calculated by dividing the span by 3 minus number of points. So as an example here, at a gigahertz signal that at the 40 kilohertz span with a 3 kilohertz resolution bandwidth, and using 1,000 points, so the calculation end up by we're having 907 hertz error on a gigahertz signal. Is very well. All of these analyzers have a frequency counter inside, and if you use a frequency counter, that 907 hertz of uncertainty in frequency will go down to 157 hertz. So if something out of this seminar or this webcast, please take note that, well, go find how to use a frequency counter on your equipment, because that's what you should be using if you want to measure the signal frequency accurately. Amplitude uncertainty, and this table is showing the treadmill equipment versus the new PXA, and EXA has similar and you can see that, well, the input didn't change much. It's half the value, but the major thing, one of the major things are the frequency response, which is now way better. Digital processing allows us to go with way better frequency response. The reference level uncertainty went from dB to 0. If you add all of them up, the D-scale fidelity, as an example, goes from 0.85 to 0.07. So if you just add them straight up to 3 gigahertz on a PXA, you'll get an uncertainty of plus minus 0.96 dB versus 5.38 dB on the traditional spectrum analyzer. Well, then that way we do we convert them to linear, and then we do the sum of the square, and that is more reflective of the uncertainty. But this is just to show you roughly the improvement achieved by the new digitizer. Example where I want to measure two signals, they are in the same frequency band, and the uncertainty within that frequency band is plus minus 1 dB. Well, if I measure a signal, I assume that it might be at one extreme, and if I measure the other one, it might be the other extreme. So if I measure a signal, analyzer, an absolute measurement, then I have to say that it is minus 1 dB. If I make a relative measurement, well, if they are really close, you can see that if they are really close, I can kind of ignore that accuracy within the band. But if they are far apart, I know this one might be plus minus this value plus minus 1 dB, and this value plus minus 1 dB. Finally, the relative absolute accuracy is plus minus 2 dB. Now, specification about the resolution. Well, the resolution is determined by the resolution bandwidth filter, or bandwidth filter. So in other words, the filter I can use, and the motion I have, but I won't use hertz all the time because the sweep time will be too slow. Another factor is the type of filter used. Now those digital filters we have today are pretty have a good CVD, so which is the ability to have a sharp edge and be able to discriminate small signal by the carrier. And phase noise, or all the noise band, is a limitation. Even if I go with a narrow resolution bandwidth, I won't be able to see that little signal here because of that. An example of the I picked a narrow resolution bandwidth filter, but I'm sweeping too fast, and there's a relationship, as I mentioned earlier, between the result and the sweep time. And usually the spectrum analyzer in couple, they will take that. But if I force it to sweep quickly, I got an error both in amplitude and an error in frequency. And I will usually get indicating that I'm doing uncalibrated measurement. Here's just a slide to show you that there has been really big improvement between the analog spectrum analyzer, that's the 8563E as an example, and the MA or the DSA as far as the sweep time. Using those nice digital IF filter, we are able to improve the sweep time by, in the case, close to over 100 faster. If we're sweeping faster, we can use narrower resolution bandwidth, and we can lower the noise for because of the sensitivity function of the or we call it display average noise level, or little channel is the minimum value that could be measured with the analyzer. This is directly impacted by the attenuator that you're using at the input. What we see here is that if we, in this slide on the right side, the attenuator is at 2 dB, and on this side is at 2 dB, and you can see that we're gaining 10 dB range into the range level. So this one here is way 10 dB more range than the previous one, just by lowering the attenuator. I kept the attenuator to 2 dB. To one chart, I said that the in order to improve the matching with the attenuator, in this case, I lowered the attenuator, but I kept 2 dB in order to get a match. Still, I go down to 0 dB, but that's not very good, and I'll add some uncertainty to my measurement. Another way to lower the display average noise level is to use a narrower resolution bandwidth. The noise is mainly thermal noise, and it's coming from the IF amplifier. And by adding a narrower filter, reduce the power of the noise going through the filter. So if I reduce the resolution bandwidth filter by a factor of 10, then I have the noise by about 10 dB. So here's some measurements for you. Here's the signal, and please note the noise level, and that resolution bandwidth will get to 10 hertz. The signal will go down, the noise will go down by 10 dB, but the signal itself will be the same. So you'll see the noise went down and the same. So the next step is let's get 1 gigahertz resolution bandwidth, and the noise will go down again by another 10 dB, and amplitude remains the same. Do a check here where we put the power at the mixer, which is actually the input power attenuator. So if you're reading on the display of your analyzer 0 dBm and you 25 dB of attenuation, then the mixer level is minus 25 dB. And on this axis, we see the signal to noise ratio in dB. So these curves are representing the noise level we have with different resolution bandwidth filter. This curve represents a 1 kHz resolution bandwidth. This one represents 100 Hz. The noise level is lower, and you get more dynamic range if you're using 100 Hz resolution bandwidth rather than a kilohertz. Looking at the same power level at the mixer. So how do I get the best this noise level or the best sensitivity? Use the narrowest resolution bandwidth I can. Put the attenuator to the minimum value. I'm averaging either video or trace averaging. Of course, if I have a preamplifier, I can use the preamplifier to boost the signal. That's working fine if you only have a small signal. If you also have a strong signal, the preamplifier is useless because it will also amplify that strong signal, and you'll get all kind of distortion. Distortion here is our mixer, and this is the signal that we want to measure. The signal comes in, it has a fundamental second and third harmonics, and that's basically what we would like to measure at the output. But if you hit the mixer with a switch is too strong, the mixer itself within the analyzer will create its own distortion, which are going to add to the signal coming in. Well, these distortions, the most common are the third order distortion, and when you have two tone, the third order is actually like this frequency component is 2 times this F1 minus this one, and it comes back in close to my 2 signals. So that's it's of interest because it will actually interfere if I got a signal close by, and that's called third order. And order is actually like harmonics, which are only like twice frequency. If you look at the amplitude, if I vary the amplitude of my tones here by about a D, well, third order will change by 3, so which means I have a slope of 2 dB. If I change by 1 dB here, this one will change by 2 dB. Therefore, the delta for a 1 dB change here, the delta is changing by increasing by 1 dB, which and for the second order, I got a slope of 2. So if we map that to the way we had before, you have the third order curve, which is slope of 2d, and telling me I hit the mixer with a signal of minus 30 dBm, I'll have internally generated third order for the spectrum analyzer at minus 70 dBc. And I would have second order signal created by the mixer of the analyzer at minus 60 dBc. So in case, well, I would like to hit the analyzer with the minimum power at the mixer, therefore I'll have the maximum damage here. So key value, if you extrapolate that third order curve all the way up to 0, which means that the intermod are at the same level as the signal come in, or your own, get the third order intermod. So that value is that specification of third order the better it is. Then the thing is done for that second order intermod, and as it reaches the zero value where the harmonics would be at the same level as the fundamental, then we call it the second order intercept. And of course, we like that value to be as high as possible. How do I know if what I'm seeing on screen is actual distortion or if it's a distortion created by the analyzer? And as an example here, I got my two signal, and the trick, we call it the attenuator test. And it is to increase the attenuation. What will happen? The noise will go up. Your signal should stay at the same point if you increase attenuation. And not only the noise goes down, but your signal goes up. Attenuation signal, the noise will go up, but your signal also goes up. It means that your analyzer was under compression, and you were measuring the right level. And if the signal you're looking at is small, it might be another signal that you don't see on screen, but it's at the input of the analyzer, and it's putting the one of its components under compression. So basically, you're measuring distortion like this. You increase attenuation until you're seeing your going up, and then that's the right level at which you should have the attenuation. But as you're going to increase attenuation, the noise will go up. At that point, it might the signal of interest, and that will be a limitation. They cannot actually measure that signal because its own distortion is as high as what you want to measure. So it is an interest of having spectral has the ability to increase its attenuation by 2 dB steps. And if you increase it by 2 dB, you may find the sweet spot in between. So with 10 dB step, you might just go and hide the signal and not be able to go and find the exact sweet spot on this display. Well, let me show it here. Yeah, here's a combination of this one is the noise level at bandwidth of a kilohertz, so it gives me the dynamic range, and I look at it with the intermod, and where the cross here, that's my optimum value. That optimum value is if the signal is minus 35 dBm at the mixer, which is my input power minus the attenuator value. For the order, in this case, it'll be more like minus 50 dB. As the mixer. So, being said, there's also the ability to measure close-in signal, and in that case, even if the analyzer has very low the average noise level, as moving in, the variation will not be the analyzer display average noise level, but it rather be the phase noise. There's a breadth of the dynamic range. So if you ask what is your dynamic range, I would say display in this case the maximum value to minimum value will be like 100 dB. So it is 195 dB. If you say between your mixer compression and noise level, then I got this range. If you say I want to measure third order, I'll say the range is 115 dB. If you say I want to measure third, I'll say, well, it's 105 dB of range. So there's no such thing as a single value. To get a best dynamic range, you get the narrowest resolution bandwidth, you get minimum input attenuation and averaging, and that's your best sensitivity. And if you measure the distortion, well, increase the attenuation until your signal stops moving, and here you have the right level. And if you want to know what the dynamic range is, well, you need to consider all the we discussed earlier. Said, let me before closing show you something nice about the analyzer. So let me show you just quickly the ability to remotely control the analyzer. So this is using Explorer. Just enter the IP address of the analyzer, and from that point I can control the instrument and get the display. Of course, ask me for a password, which is in case by default measure for you, and then you have the live display of the analyzer. also allow me to go and get an image. I can grab a save call setup, and actually I can display with someone else in the in my group. So that's about what I wanted to cover during this presentation. So,
well, thank you very much, Andre. That's been a really informative presentation. If there's questions, we can unmute, or got a couple. What's that last display that you showed, Andre? And you said you can share that display. This is the remote connection. You can share that display with your colleagues. Does that mean that if multiple people connect to the same IP address, would they all have live control of the instrument, or one person acting the other people servers?
Yeah, that's the thing. I never tried to have more than two. So I can control it from, if I connect remotely, I can control it from my PC, and the person in front of the equipment can also control it. Never tried to connect two persons to the same instrument. That will be something I need to try.
Oh, and then just a couple of questions regarding some basics. This is a great presentation, in my opinion, for demonstrating the considerations a researcher has to take into account when setting up their signal or spectrum analyzer to make measurements. Now, if one was measuring the output of a mixer, how can the harmonic components from the mixer, say from alias components that might be coming down from the sampling, is that taken care of with the input filtering?
Well, it's a very interesting question, because if you look at the spectrometer block diagram, so let me in one of them I've shown that there is a preselector, and that preselector actually will take signals away if they are far enough. If they are close,
okay.
So here's my preselector. So, example on the AXA, there's no preselector below 3.6 gigahertz. It's a low pass filter. So if you have a signal at 1 hertz and a signal at 2 gigahertz, both are seen at the input of the analyzer. In that case, you have to be careful that you're playing with the attenuator to identify if the signal is coming from the device or coming from the spectrum itself.
Yeah.
If it moves, it was coming from the analyzer. If it's when you move the attenuator, it's coming from your signal.
Okay. That the spectrum analyzer always captures its full range of points, which I think is 40,001, and then just display the number of points these are select.
Right. It shows more than that. To find out, depending on the board you're using, the IF digitizer option you took, digitizer might digitize at 400 megasample per second, and depending on the number of points you took and the resolution bandwidth, then the sweep time will be slower, and then the number of points that will capture will vary. The 4001 is the maximum number of points you could display, and in some cases it might be the number of points that were captured, but usually it captures more than that.
Okay. And when averaging, can users select to average point by point, or should it always sweep by sweep?
Averaging point per point is really what the video bandwidth does.
Okay.
So by reducing the video bandwidth, they're kind of doing a point by point averaging.
Okay. And then you mentioned that the sampling rate of the AC is about 400 megabits per second.
That will vary depending on the ADC the option you're taking on the analyzer.
Okay.
So, as an example, the board that digitizes on a bandwidth of 160 megahertz has ADC of 400 megahertz. But if you take the 25 megahertz option for bandwidth, then digitizer will be slower.
Okay. And I hate the time that you spent on discussing the measurement uncertainty and how the settings of the analyzer itself affect the measurement uncertainties. I think that's a very important point for researchers to take into consideration. It's very tempting always to, when using an instrument, measurement, and just consider that that's the measurement, but we should always be considering that it's plus some amount of measurement uncertainty. And just wondering, in terms of setting the reference level when looking at an input signal, how important is that setting? Do you tend to move your reference level such that the peak of signal that you're measuring is up near the top of the display, or does it have an impact on the...
It doesn't have any impact anymore, because in the past, we were always saying people should actually put the reference level to the top of the display, that the log amplifier was calibrated at the reference level. And as you would move away from the reference level, then you will include some errors. Now, since the log amplifier is completely digital, the reference level is actually just a display function, and there's no uncertainty, as you can see here on this.
Okay, you'll adjust your reference level if you're lowering your dB per division of your scale, so that you can have a range of the signal.
At a wider range,
just for the display.
Because even though even the display scale fidelity is very small compared to what it was before.
Yeah. And, one question, if you don't mind, is just what conditions might there be in measuring absolute power with a spectrum analyzer versus, say, a power meter? Well, looked at is some of the amplitude accuracy considerations.
Yeah, that's a little scary. Yeah. But with no some fears. It's always in that way as far as the accuracy. As I mentioned earlier, just by adding the dB, it's not a very nice way of doing it. The best way will be to convert them to linear and then do the square of the sum of the square. But to answer your question, why would I use a spectrum analyzer rather than a power sensor? Well, sensor is broad. It'll have better accuracy as far as amplitude, but it's not selective. If I want to make a signal-to-noise ratio measurement, I cannot really use the power sensor. And if I want to know the absolute power coming out of my transmitter, including everything, then use a power sensor. But you could couple a power sensor with your spectrum analyzer and actually take a known source or a CW source and bring it to the frequency of interest. As an example, you bring it to 10 gigahertz, you go with a power sensor, and then you can fill a correction table on the spectrum analyzer. And in doing that, you're kind of eliminating the frequency response uncertainty, because you're not relying on the 50 megahertz signal calibration to calibrate the equipment, but you're actually using own source, which you are actually measuring with the sensor.
Yes. Well, thank you very much. If there are other questions, with that, we'll conclude our webinar, and I'd like everybody to join me in thanking Andre Beaulieu for an excellent presentation today.
Thank you.
Thanks.
Thanks. Bye.
And goodbye.
Bye.